0.5, and now we're not showing two expressions are equal, but we've set two non-equal expressions to each other, and we want to find the value of x that makes it a true statement. And that's solving trigonometric equations. This is all about solving trig equations. Well, we want to point out a few observations. I'm going to go to the textbook and also point out a typo that I discovered while I was looking at it again. There's always typos, and I'm trying to correct them as I go along. I've got a ton of rabbit ears on my pages, and I've corrected little typos throughout the finding the book. But let's take a look at this section. And also save us some in the interest of time here. So everything we're going to cover is pretty much out of the book. So it's trig equations. Oh, let me go back to the pre-calculus text. Now, one of the things that's different about trig equations and algebraic equations, in algebraic equations, polynomials and things of that nature, we typically have a finite number of solutions. You don't have more than a fixed number of solutions. And it's, as we saw, it's dependent upon the degree of that polynomial, the maximum number of real solutions you can get, but we also had imaginary or complex solutions involved there as well. But with trig, since they are periodic, you could have infinitely many solutions. So for example, let's take a simple trig equation, sine of theta equal to 0. And they don't give you any information, they just say solve that. Well, since that goes on and on, we know it's 0 when theta is 0, when it's pi as I move to the right, 2 pi, 3 pi, 4 pi, 5 pi, if I'm moving along the right, along the x-axis. But I also could go in the reverse direction, move along the, to the left on the x-axis, or the theta axis, I should say, minus pi, minus 2 pi, etc. So in essence, there are an infinite number of solutions over here. And it's equal to, theta is equal to 0 plus or minus n pi, where n is 1, 2, 3, etc. So I get n is 1, so I get plus pi minus pi. N is 2 plus 2 pi minus 2 pi. So I have an infinite number of solutions to that. Well, what oftentimes happens is you only want solutions in a smaller range of possible solutions. For example, you might set a restriction on that on where you want to find your solutions. Maybe the restriction is between 0 and 2 pi, inclusive, and not inclusive of that. Or maybe it's between minus pi over 2 and plus pi over 2. If that's the case, then you have to pick the finite number of solutions out of this set that satisfy that condition. Now, I want to make a little correction over here. There's no n in the cosine over here. There's no n in the cosine, and more importantly, the arc cosine of 0 is not 1; it's pi over 2. That's a typo in the textbook there. So we'll kind of make a note of that. Now, what I do want to do is talk about some of the fundamental questions that anytime you're solving a trig equation, you want to address and at least come to some answer or resolution on. Anytime you see a trig equation, they're asking you to solve it, not to show two expressions are equal. Again, same equal sign, totally different meaning. When you have an equal sign and you're asked to solve the equation, instead of show that they are saying, this is what your mindset wants to switch to. First thing you want to know, am I looking for an answer in degree or radian measure? They should always take that into account. In the calculus, when you see an x, you're pretty much always in radian measure. When you see theta, a lot of times it's probably degree measure. Not necessarily, but you have to understand that. So that's a partial giveaway. X is radian, theta is probably degrees, but not necessarily. Now, is the range of possible solutions restricted in some way? Are we looking for an infinite number of solutions? Or are we looking for a finite number of solutions? Many times it could just be one solution. Maybe they refine so much that there's only one real solution. And here, we're only looking for real solutions. And that's the only case we have. It's real solutions. We're not going to be looking for complex. It's real numbers. And then the other thing is, can we find an exact solution? Is it one of those special angles that we're working with? Or are we looking for an approximate solution? If exact, we'll have to do some additional analysis to find the solution. I usually go to the unit circle. And there's a cheater's way around it. If it comes up, I'll show you the cheater's way around that. It's a shortcut. But I like the unit circle to kind of give me the indication of the exact solution. Now, if it's approximate, we can use our calculators and the inverse trig function to solve. And also you have to consider, does it even have a solution? There may not be a solution because that trig function may never touch the x-axis. So you should always be considering all those possibilities when you're solving a trig equation. Okay, so let's take a look at that. I'll take a look at some examples now in the remaining 11 minutes that we have here. So let's start with a very simple one that we're all comfortable with. And say we're looking for the following. Let's see. Okay, a simple one I have in the book. We'll do two of them. So I have sine of theta is equal to 1/2. Okay? So this is my first example. So we want to find all the values of theta. Now, what sine of theta is. In this case, all the values of theta, but we're going to use, in this case, we're going to get radian measures. We're not going to use degrees, but I'm going to use radians. Even though it's theta, I still want to use radians to kind of show you what's happening. Well, the one way to think about this is to, again, go back to our unit circle. I mean, you can plug this into your calculator, and I'll show you the cheater's way of finding it in a second here. But here it is, and then we're looking at, this is my angle theta. Here's my unit circle. And here's my angle theta. So I'm moving along this unit circle, and we want to find out all the values when the sine, that's the y coordinate, is the value of 1/2. So I can see I got this angle over here. Then when I flip it around, I got this angle. So this angle over here, you may not realize this is pi over 6 or 30 degrees. So this first angle over here is pi over 6, which is 30 degrees. So one solution. Since I didn't give you any information, there's no restrictions. I'm looking for all the solutions. What I have is that theta is equal to pi over 6. Then I have this solution way over here. Well, that's pi over 6. This is also pi over 6. This is pi. When I go all the way over here, that's pi. Pi, which is 6 pi over 6, minus 1 pi over 6 gives me, in this case, 5 pi over 6. Okay? And then what I can do is I can, if I'm here, I want to get back to this all the way around again, I can just add, this is a solution, but if I go around one complete cycle, I'll start here and go all the way around, because I can keep going around and around that circle. That's why there's infinitely many solutions. Well, that's another 2 pi, so I can add 2 pi to pi over 6. Well, this is going to give me, in this case, you can add, this is 12 pi over 6. 2 pi is 12 pi over 6 plus, pi over 6. That gives me 13 pi over 6. So I have another angle over here, which is 13 pi over 6. Here I could also go around another cycle of 2 pi and add that to 5 pi over 6. So I could take 2 pi plus 5 pi over 6. Well, this is again 12 pi over 6 plus 5 pi over 6. So you can see where it's complicated. You have a lot of solutions to find. That gives me 17 pi over 6. They're all giving me my y coordinate, which is a sine, giving me 1/2. But what also makes it complicated is if I could go around in the opposite direction. So I could start here and go all the way around over here. This is, okay, this is 6 pi over 6. This becomes a 1 more, that's negative. So now I can look at the negative angle. This is going to keep going, in fact. You know, I can keep going around another 2 pi, another 2 pi. Just keep doubling and doubling and doubling those. But I could go around in the clockwise fashion. If I go clockwise, my angles are negative. So this has all been counterclockwise. But I could also go in a, you know, clockwise fashion and hit that point, and then hit that point. So this is over here, this is 6 pi over 6 plus 1 more, 7 pi over 6 with a negative. So it's negative 7 pi over 6. And then I could go a little bit more over here. This is, you know, pi, so this is minus a negative 11 pi over 6. And you can kind of see what's happening over here. Let's just put it in plus and minus now. This is complicated. You have to look for a pattern. So when I don't give you restrictions, there's infinitely many solutions. Can I put it in a pattern that is recognizable? So let's start putting them in, you know, kind of the order that we might see over here. So we can start with, okay, so I'll put them in theta, and I can see if I have a pattern. I have my smallest angle, pi over 6, and 5 pi over 6. And then I have my minus 7 pi over 6. And comma, this is the next smallest angle, minus 11 pi over 6. And then we're going to have my 17 pi over 6, right? I'm going to have 2 positive ones there, so 17 pi over 6. And then we'll have the next one, and we'll start to see, you know, this will be plus, so 2 pluses, 2 minuses, 2 pluses, 2 minuses. Now, if we try to kind of work with that, it's hard to see a simple pattern, what you're going to have over here. So if you just wrote this, this is good enough. And it shows you there are infinitely many of them, but that captures most of the behavior. So here there's no easy pattern. I mean, there is one that I could get from this. I'd break this as, you know, 1, 7, 17, and I'd set up a way of doing that, and 5, minus 11. I'd do a plus and minus sort of thing that would be going. I'd have my, you know, minus 1 to the I sort of thing for that, and 2 things. But I'm not going to do that. It's just too complicated. But at least we show that we know we can keep going on forever. Meaning, flip around another 2 pi from each of those locations, either in the counterclockwise and the angle is positive, or clockwise and the angle is negative. So it is complicated. A very simple equation, very simple equation, yields to, in this case, a lot of complicated solutions here. Okay, that's one. Now let's take a look at some that might be a little bit easier. Maybe they're going to restrict the domain. So that's where my domain is not restricted. So I'll just do one more for the unrestricted, and then you can kind of see what's happening. And you can also, I should say, you can also look at this using your calculators, or I would prefer to use the online app to kind of see what's happening there. And I'll show you roughly how to do that as well. So let's take a look at a second example, which we have cosine theta times the sine of theta is equal to 0. But now we're going to be restricted over here. We're going to say that your theta has to go between, so 0 is less than or equal to theta, which is less than 2 pi. Not equal to 2 pi, but strictly less than 2 pi. So that's our restrictions. So we're looking for when, in this case, since I have a number times another number, and their product is 0, I can use that 0 factor property, and I know there's 2 possibilities. I'm either solving for the cosine of theta equal to 0, or the sine of theta equal to 0 on that interval. Because then if this is 0, 0 times the number is 0. That's 0, 0 times the number is 0. They're both not 0 at the same time, so we know that. So let's start with the cosine. And again, you can either draw the graph or draw the unit circle. It doesn't matter. So over here, here I am, a unit circle. And what do I want? I want to find out when my x value is 0. And there are two places that occurs between 0 and 2 pi, and there they are. So I have pi over 2, positive pi over 2, and 3 pi over 2. I go 90 degrees and 270 degrees. So this gives me, there is pi over 2 or 3 pi over 2. Well, what about the sine? I'm now looking for my y coordinate being 0, so I want my y being 0. Well, on this interval, I have two possibilities, and they occur, right here and right there. So what do I get? Theta equals 0, or theta is equal to pi, and it's on that interval. So I actually have 4 solutions between 0 and 2 pi. So let's take a look at that, and that's what I'd write there for my solutions. I don't have to consider infinitely many solutions anymore. I'm done. It's finite. But if I want to say, look at, say, something like Desmos, and I wanted to do that, let's see how we might look at that. And we'll close out with this. We're pretty much done for now. You just look through the book for some other things if you need some extra assistance. Let's take a look at the first one I put over there. I had my say y equal to the sine of, I'll just put it, well, let's just do the sine of x equal to 1/2. Sine of, two ways of looking at it. Sine of x equal to 1/2. I don't know if it's really going to give us much. It's just giving me these values. Rather than doing that, let's show it graphically. Y equal to the sine of x, and then y equal to 1/2. Where these two graphs cross, that's where my zeros are. And you can look at where they cross, and it's giving me in the radian measure. So there's my pi over 6, 5 pi over 6, 13, 17, going the other direction, -7, -11. So that's much easier than the analysis I did. So that's why the beauty of using Desmos. It kind of really captures that. But you need to reason through that. That's why I like the unit circle for reasoning. Now let's take a look at this other one. So let's do y equal to, let's get rid of this guy here, cosine of x times the sine of x. Cosine of x times the sine. Okay, so that's when these are 0. But my restriction over here, I'm restricted to just stay from 0 to 2 pi. So x goes from 0 to 2 pi, and let's go to step as, pi over 4, whatever. And let's just make this go from minus 1.5 up to 1.5. Okay, so this is what we have, and I want to find out all the zeros. So 0 is inclusive, and I might have to go make this just a little bit less than 0. So minus 0.1. So over here, that is a solution. So I'm just looking for the value. This is the first coordinate. Pi over 2 is a solution. Pi is a solution. 3 pi over 2. So all those angles. Now 2 pi would be a solution, but notice when I write this out, the 2 pi is not included. If you look at the board again. Let me just kind of go back to that. So over here, we're not expressly including 2 pi, so I don't have 2 pi over here, meaning all the way around. So these would be the only 4 solutions. So you can see how I did it analytically and how graphically. Now, using your TI calculators, it's not as sophisticated as that. It doesn't give you in pi, it gives you the radian measure in decimal form, and that's what makes it a little bit more complicated. Okay, so we're out of time.